When we train AI models to generate videos, we usually start by compressing raw pixels into a compact latent space using a video autoencoder. However, traditional autoencoders are optimized almost entirely for pixel-level reconstruction. This means they focus heavily on local textures, colors, and fine-grained details, while ignoring high-level semantic organization. Because the latent space lacks structure, the downstream generator has to spend massive computational effort rediscovering basic concepts like objects, actions, and scene layouts. V-RAE rethinks this paradigm by building a generative latent space directly on top of frozen vision foundation models. To understand why this matters, we must realize that good reconstruction does not guarantee good generation. A standard autoencoder might reconstruct real videos perfectly, but its latent space can still be highly curved, discontinuous, and incredibly difficult for a generator to navigate. When a diffusion model tries to learn this chaotic space, it struggles to generate coherent new samples. By contrast, a semantically organized latent space groups similar concepts together. This makes the generator's job much easier, allowing it to focus on how visual states evolve over time rather than struggling to decode disorganized pixel representations. Let us look at the V-RAE architecture. It begins with a frozen vision foundation model, such as DINOv3 or VJEPA, which acts as the encoder. Because these models process frames independently or with minimal temporal compression, they produce temporally dense features. To make this computationally affordable for generative modeling, V-RAE introduces a learnable, lightweight temporal pooling module. This module compresses the features along the temporal dimension. Finally, on the decoder side, a spatiotemporal transformer decoder equipped with 3D rotary position embeddings reconstructs continuous, temporally coherent video frames from the compressed latents. The key to compressing video features without losing their semantic meaning lies in the temporal pooling design. Simple mean pooling preserves semantics well but results in poor reconstruction because it cannot adapt to rapid motion. Conversely, convolutional pooling improves reconstruction but destroys the semantic structure. V-RAE solves this trade-off using temporal attention pooling. With only 3 million parameters, this content-adaptive module uses a shared query vector to selectively weight and aggregate features. This achieves an optimal balance, keeping the latent space highly decodable while retaining over 89% of the original encoder's semantic probing accuracy. To evaluate how well a latent space supports generation without training a full diffusion model, the authors introduce a new metric called temporal freshet video distance, or tFVD. Standard reconstruction metrics only test the model on exact encoded data points. tFVD, however, deliberately breaks this path. It replaces interior latent codes with the midpoint of their temporal neighbors and decodes the interpolated sequence. If the latent space is smooth and robust, this interpolation decodes into a coherent, natural motion. The authors found that tFVD correlates much more strongly with downstream generation quality than standard reconstruction metrics. When put to the test in class-conditional video generation, V-RAE variants consistently outperform conventional video Vs. On the UCF 101 and Kinetics 600 datasets, V-RAE achieves significantly better generation quality. More importantly, because the semantic latent space is so much easier for the generator to learn, V-RAE converges up to 6 times faster during training. For example, a generator trained on V-RAE latents can reach a high-quality generation threshold in just 30,000 updates, whereas a generator using a standard VAE latent space requires 150,000 updates to achieve comparable quality. V-RAE's benefits extend beyond standard video generation into visual world modeling, such as future video prediction. When tested on the cityscape's driving dataset, a predictor operating in V-RAE's semantic latent space significantly outperformed the baseline 2.2 VAE. Even though the baseline VAE has better pixel-level reconstruction, V-RAE's semantically organized and temporally smooth space prevents structural and identity drift over long horizons. This allows the model to predict realistic future frames that maintain sharp vehicle contours, clear lane structures, and distinct pedestrian boundaries. In conclusion, V-RAE demonstrates that frozen semantic representations from vision foundation models can support high-fidelity video reconstruction, rapid generation, and predictive modeling. While current experiments are focused on controlled benchmarks, future work will explore scaling V-RAE to large-scale, open-domain text-to-video generation. By shifting our focus from pure pixel reconstruction to semantic organization, we can build video generators that are not only faster to train, but also far more capable of understanding the physical and semantic structure of the worlds they create.